Right, so this is the first video for the polar functions unit, and it's actually the last unit that you will be tested on the AP exam. However, we do have one more unit after this for, it's basically topics that the state of Texas requires us to teach for the course of pre-calculus. So we have one more unit after this, but this is the last topic that you will be assessed on the AP exam. First, we're going to start with a couple reviews. What is a radian? This gets lost. We go between degrees and radians, but people just usually work with radians without actually understanding what it is. So imagine that the radius of a circle is a noodle. So the radius of a circle is a straight line from the center to the edge of that circle. Basically, if you were to boil this noodle, so say that this is our noodle here, it would become softer to where you could line it up against the edge of that circle. And basically that part of the circle that the radius covers is going to be equivalent to the length of the radius, even though it's now bending. So it can be shaped to match the arc length along the same circle, all right? And if we were to take that arc length and push it across the circle, you would get three lengths of that radius. And then you would have this little section here that would be the 0.14159, which is going to give us the irrational number of pi, all right? And that's why we say that we have pi radians, or 3.14 radians, is equivalent to 180 degrees, because we have three lengths of the radius plus that 0.14 that is equivalent to 180 degrees, which is why the units is radians when we are in radians. We don't usually write radians, it's like invisible, but in degrees we always include the degree symbol, so that's how we differentiate between the two, all right? So something that we need to remember, you will see it, is that the arc length of a circle, arc length is usually written as S, and that's equal to theta times R. So the first thing that we need to remember is that theta is the ratio of two lengths. And we talked about this before in a different unit. It's the ratio of two lengths. It's the arc length divided by the radius, which is equal to 1 radian. And this is the result in a unitless measurement, because the arc length is in, say, we'll call it feet. The radius is also in feet. When you divide those two, they cancel out. However, radians are used to represent a ratio as an angular measurement. And basically we get 1 radian when the arc length is divided by the radius, and it's equal to 1. All right, so why do we use pi? So the number pi, which is about 3.14, that's the famous abbreviation, it represents the ratio of a circle's circumference to its diameter. And since the circumference is 2 pi r, it takes 2 pi, which is about 6.28 radii, to go around the entire circle, no matter the radius, okay? So we have a circumference here of 2 pi r, and then that means we'll say that this is pi, so pi is the top part, and then we'll have another pi at the bottom, which is 2 pi. Which is why 2 pi is equivalent, or the approximation is 6.28 radians. So a couple decimals or abbreviations that you should get comfortable with is going to be 180 degrees is going to be pi radians, which is approximately 3.14 radians. We have 90 degrees, that is pi over 2 radians. In decimal form, that is 3.14 divided by 2, which is about 1.57 radians. 60 degrees, we have pi over 3. That's going to be about 1.04. And then 45, that is pi over 4. That's equivalent to 0.78. 30 degrees, that's pi over 6, equivalent to 0.52. And then 360 is going to be 2 pi, which is about 6.28 radians. Okay, so these are just some important ones that you should recognize if you were to see them in decimal form. And something else that we should talk about is, so we have this graph here. We have it centered at the pole, and we have concentric circles, which means all of the circles are centered at the same point, which is the pole here. So we're going to start calling this the pole. It's no longer the origin. And then we also have the polar axis here. So with these concentric circles, if I align the radius and then draw that same curve along the edge of the circle, and it's equivalent to the arc length, I'm going to have the same angle for every single circle here. All right, so theta is going to be the same for all of these. Whenever the radius is equal to the arc length, it is going to be 1 radian. And that is actually about 57.3 degrees. And that's the same for any circle. So that's translating 1 radian from radian to degrees. It is 57.3 degrees. All right, so this is our introduction to polar. And the reason why we have polar is because not everything is going to work in rectangular. We don't always move to the left 1 and then up 5. We have to work from a point, and sometimes we need to extend out and then open up depending on the angle. And a great example of this is ships, all right? And planes and anything that has motion that is not linear, it's more convenient to do in polar. So there's all this that you can read if you want to dig deeper into that. That is there for your enjoyment. But we're going to start by just plotting, all right? So I want to plot a few points here. So say that we have the first point. Now in Cartesian, and this is basically what this is explaining here. In Cartesian, we have x, y. We have the horizontal factor and then the vertical factor. In polar, you're going to have your radius, and then you will have your angle, okay? Now, the polar grid is scaled as the unit circle with the positive x-axis now viewed as the polar axis and the origin as the pole. So when you're in polar, we aren't dealing with the origin anymore. We are dealing with something that is called the pole, and that is at the center of our concentric circles. And then we have our polar axis, which is here. We use all 4 or these 2 axes in order to help create a bond between Cartesian and polar. But really, when you are drawing a polar graph, this is all you see. This is what you start with, the pole and then the polar axis. And then this is how we plot the points. So based on the radius and the angle, I'm able to plot a location along these concentric circles. So if we have a radius of 3 and then an angle of pi over 2. So the unit circle would be a radius of 1. That's what we see at the center here, all right? So we're going beyond that now, but we're going to use attributes from the unit circle to help this. If I have a point that is 3 pi over 2, I'm going to extend out 3. So 1, 2, 3, and I'm on the circle with a radius of 3, and I'm going to open up pi over 2. So that means my coordinate is here. And I like to draw little orientations to show which way we're going, because sometimes we might open up in the opposite direction. And we'll label that as A. The second point, let's look at radius of 2. We're going to open it up with an angle of pi over 3. So now I'm going to go out 2, radius of 2, and I'm going to open up to pi over 3, which would be here. Actually, it's a little bit closer to pi over 4. We'll say here. So that is B. And let's do this last point. We'll call it C. We'll do negative 2 pi over 6. So now we're looking into something or a negative radius, which we haven't really explored a lot, but we're going to treat it just like we do on the x-axis. So I'm starting at the pole. Now my positive radii, I move to the right. For negative radii, you will move to the left. So I'm going to travel negative 2. Now, pi over 6, a positive angle will always open counterclockwise, all right? always, no matter what side of the pole that you are on, you will open counterclockwise. Negative angles will open clockwise. So even though I'm on the opposite side of the polar axis, I will open an angle of pi over 6. Now, if I think of pi over 6 in the first quadrant, it opens up this much, okay? And then if this is pi over 4, which is what we see on the grid, it's just going to be a little bit before that. So I am going to open up in the counterclockwise direction, which means my point will be here. So that is my point C. So be careful when plotting these. If it's positive, if it's a positive angle, you will open counterclockwise. So an important note, rectangular coordinates x, y, the x is the independent variable, the y is the dependent variable. However, in polar, they switch. R is the dependent variable and theta is the independent variable. We switched it here because it's easier to plot using the radius first and then opening up and sweeping, opening up that area. However, as we go forward, theta is the independent variable. Think of it as the input, and then R is the output. All right, that's a common misconception for students. Now, a activity that I have is this, and this link, you can just type it in if you want. It's great practice, and it gets away from like the monotony of the notes. Basically, you're looking for a ship, all right? It's pinging, and I can see, okay, well, I see that it's opening up in quadrant 3, which means it has to be beyond 180 degrees. So this is me standing at the pole, and that thing is going away. Let's slow it down. So you're standing at the pole at home base, and you're looking for this ship that maybe it's lost or something. It's the power one. I don't know how they work. But I'm looking, and I don't see it yet, but I know I'm supposed to be in quadrant 3, and then I see here. So 260 degrees. Great, because that's really close to 270. I know that this is going to be right. But now you have to figure out, okay, how many, I think we're doing knots, is it? I don't know how far that is. Now we want to know how far. It's not 1. If I look on my concentric circles, I see that it's 1, 2, 3, maybe it's 4 out. But I can see as I get closer, the focus gets better. So this is a great way to kind of just, okay, if I'm in different parts, and you can keep hitting reset in the top right corner to kind of play around with it. Now I'm at 0 degrees, but now it's really far. It's like after 9, maybe it's at 10. Yes. All right. So this is a great way to get used to how far we're opening up within the polar coordinates. And you can even jot down your locations if you want. Okay. All right. So this is coming back to basically AP pre-calculus. This is where we started last year, but I think talking about what we're doing and how we're approaching it is going to be important. So it says plot and label the following polar coordinates on the polar coordinate grid above. So I have 2 pi over 3. So remember, we are plotting 2 pi over 3, but pi over 3 is the input, the angle is the input, the radius is the output. A way to remember this is think of r equals sine theta. The independent variable is theta, the output is r, all right, even though r is listed first. So I'm going to travel out radius of 2, and I'm going to open up to pi over 3. So we are plotted here. This is point A. And I'm using the orientation to show where we're going. All right, point B is 1, 3 pi over 2. So I'm going to travel out to a radius of 1, and then I'm going to open up all the way to 3 pi over 2. And again, my angles are positive, so I'm opening up anti-clockwise. I'm sorry, counterclockwise. All right, part C, we have a radius of 3. And I'm going to open up to 4 pi over 3. Let me label this as B, though. And then 4 pi over 3 is going to be in quadrant 3 over here. Now, notice that it's not the closest angle anymore, 2, 3 pi over 2. If we look at our concentric circles, we have some extra lines in here. This line here is going to be pi over 12. All right. And then this line up here is 5 pi over 12. Essentially, all of your angles can be written with a denominator of 12. 6, 4, and 3 are all, 12 is divisible by all 3. So this is technically pi over 12. This is 2 pi over 12, 3 pi over 12, 4 pi over 12, 5 pi over 12, and then 6 pi over 12. They continue to go all the way until we get to 24 pi over 12, which is 2 pi. So when you're plotting, you have to be careful. This line is new, and this line is new. Your three familiar angles will be the middle three. All right, so look for the middle one, which is pi over 4. And then on either side, it's pi over 3, pi over 6, or the families. And this should be okay to you because we've worked with 0, 30 degrees, 45 degrees, and then 60 degrees. This increment was 30. This one was 15, 15, and then the next increment to 90 was also 30. So now we're playing around with 15 degrees, and then up here we have 75 degrees. Okay. I wish we taught it like this at the unit circle level, but it's not how it's taught normally, so we didn't. But now you're going to see those family of 12s everywhere. The last one that we're going to look at is D. It's going to be 2, so we have a radius of 2, and it's negative pi over 6. So now I'm going to rotate clockwise, and I'm not going to stop here because that's my pi over 12. I'm going to go to the second spoke. That is my negative pi over 6, so that would be D. All right, example 2, plot and label the following polar coordinates on the polar coordinate grid. If I have A, I have a radius of 2, and I'm opening up to pi over 4. All right, part B, we have 2 negative 7 pi over 4. So I have a radius of 2, and now it's negative, so I'm opening up clockwise. So 7 pi over 4, if I think about the positive, I pass 1, 2, 3.5 quadrants. So I'm going to do the same thing in the opposite direction. I go 1, 2, 3.5 quadrants, and I'm actually going to be coterminal to the first one. So this point is also B. C, I have 2 9 pi over 4, so I'm going to travel 2, and it's positive angle, and it's 9 pi over 4. If I think about that, 2 pi in terms of a denominator of 4 is 8 pi over 4. So I'm going to open up a full rotation. And then I have 1 extra pi over 4 left. Oh, that's cool. I didn't know I could do that. I have another pi over 4 left. So I'm going to open up. This circle is going to make me mad. How do I get rid of it? Oh, so I open up another pi over 4. So that is also C. And then you can probably guess the last one, D, is going to align as well. We go negative 2, so we're traveling to the left. And now we're opening up 5 pi over 4. So I'm going to open up counterclockwise. So if I think of pi over 4 from standard, I pass 1, 2.5 quadrants. So I'm going to do that in the opposite direction. So I go 1, 2.5 quadrants. And now I have the last one. So these are all the same coordinate point. And this is very important in polar. In Cartesian or the XY plane, each point has one representation. If I want to get to 1, 1, the only coordinate I can do to get there is use x equals 1, y equals 1. However, in polar, there is an infinite number of representations to hit one point. All right, so this is why we're going to be switching how we understand about graphing, is because this is completely new. We have an infinite number of angles for this particular point. Therefore, there's multiple representations for it. Okay. So number 3 says plot the point with polar coordinates 3, 5 pi over 6 on a polar grid to the right. Then write the polar coordinates for the point 2 different ways. Okay. So we have a radius of 3. So I'm going to extend out 3. And then 5 pi over 6 is in quadrant 2. So I'm going to sweep all the way to here. Hold on. We have... Yeah, so this is pi over 6. Remember, there's a spoke in between now. It's our family of 12, so be careful with that. So I know 5 pi over 6 is next to 3 pi over 4, so I'm going to go past one spoke for 3 pi over 4. I think I messed that up in my key. I'll fix that. All right, so now we want another way to write this. So a classical way is to extend out 3, and then instead of going counterclockwise, we go clockwise. And we end up here. So I still have a positive radius, and then I am traveling counterclockwise. So if my radius is positive, it's still positive 3, but now I'm at 5 pi over 6, but traveling the opposite direction. I started at, we can say, 2 pi, and now I want to subtract or go in the negative direction. So I also can look at this as, okay, what if I start at 5 pi over 6, and then I go around and I subtract 2 pi. So that's one way to find out what this angle is. Now, to rewrite this, we need a denominator that matches. So we'll do 12 pi over 6, which means 5 pi over 6 minus 12 pi over 6 is going to be negative 7 pi over 6. So that is another way to write that coordinate. So on this side over here, theta is equal to 5 pi over 6. And then if we go the opposite direction, theta is equal to negative 7 pi over 6. Another way to write this, probably a more convenient way, so we're not having to add and subtract from or with 2 pi, is travel in a negative direction. So we can have a negative radius of 3. And then I will open up to this coordinate, which, because I'm traveling clockwise, that's going to be a negative angle, and it is negative pi over 6. So those are our 2 points that align with the coordinate point 3, 5 pi over 6. So an important note is that rectangular coordinates, so x and y, a point has only one representation, and then a polar coordinate has infinite representations. So this is what I was talking about up here, is that between Cartesian and polar, this is a huge, huge difference, all right, that you have to be careful with. All right, the last part of this video is connecting rectangular and polar coordinate system. This is one of the most important things that you will learn in this course, all right? So if you recall from the previous unit with complex numbers, we talked about trig form a lot, where A was equal to r cosine theta and B was equal to r sine theta. We are going to continue this. So complex numbers is the bridge from Cartesian to polar. So that's why I was emphasizing if you were struggling with complex, you're going to struggle with polar. So you have to make sure that you practice so that you don't end up slipping behind. So if we take a look, if we start in rectangular, we can only move in 90 degrees, all right? So I have my x and I have my y, I get to my point. Very restrictive, all right? But if we think about this in polar, we start from the pole, we have our radius, and we have our angle, and we are able to get to a point. So now we can extend out and then travel along a circular path in order to get to our coordinate, all right? The connective tissue for this is going to be Pythagorean identities, all right, or Pythagorean theorem, okay? So we have our pole here, we have our radius, and we have our point A. We can also connect that by seeing the change horizontally and the change vertically, okay? And in order to connect these three, we have our Pythagorean theorem. So r squared is equal to x squared plus y squared. Now do I want to show it? I think I do. Let's go ahead and show it. I will show the where we get these formulas from. So I have r squared, which is equal to x squared plus y squared. How did I do this before? Let's see. Pull it up real quick. Actually, I'll just show it from my calculus class because I showed it to them when we introduced, let me see, in the polar. Parametric and polar, notes packet key, because I don't think I have enough space for it. Okay, here it is. So we have x squared plus y squared is equal to r squared. Now, I can't write on this, so you'll just have to look. Now, talking about x is equal to r cosine theta, so we can plug in r cosine for x. Y is equal to r sine theta, so we can plug that into r sine theta, okay? Or plug that in for y. And then if you square both of those terms, we have r squared times cosine squared plus r squared times sine squared equals r squared. Factor out the r squared, you get cosine squared theta plus sine squared theta, which equals r squared. Therefore, cosine squared plus sine squared, that's a Pythagorean identity, that is 1. Therefore, r squared is equal to r squared. So we're back to where we started. So this isn't, I'm not going to ask you prove it, but this is how and why this conversion works. It's not just because, oh, it was like some crazy math. It's literally just using identities and some distribution, okay? All right, so the formulas that you will need to remember is that, pull this back up. So the first one is going to be that r squared, and we might as well number these. R squared is equal to x squared plus y squared, and by extension, r is equal to the square root of x squared plus y squared. The second one, this is stemming from complex numbers, but now we're going from rectangular to polar. It will be y is equal to r sine theta. And by extension, sine theta is equal to y divided by r. The third one is going to be x is equal to r cosine theta. And by extension, cosine theta is equal to x over r. And this is what we use to convert between these two dimensions. All right, so going from rectangular to polar, polar to rectangular, we can do this. Just like in complex numbers, when we went from rectangular to trig, this is what we're going to use for rectangular to polar. So convert the following points from polar coordinates to rectangular. We have 2 pi. All right, so my r is equal to 2, and my theta is equal to pi. So remember, coordinates, it's r theta. Even though r is the output and theta is the input, r is listed first in polar, okay? All right, so if I want to convert to rectangular, I need to solve for x and I need to solve for y using r and theta. So x is equal to r cosine theta. So my r is equal to 2 and my theta is pi. If I think about the unit circle, I'm over here. Cosine of pi is going to be -1, so I have 2 times -1, which means my x-coordinate will be -2. For y, it's going to be r sine theta is equal to 2 sine pi. Sine of pi at that same point will be 0, so I have 2 times 0, which is equal to 0. So that means my rectangular coordinate is going to be -2, 0. So if we think about 2 pi, I go out 2 and I open up pi, that puts me over here. And then if I think about -2, 0 in rectangular, I end up at the same coordinate. So they will overlap. So these are equal representations for the same point, depending on what plane you're working in. So now we have 4, 5 pi over 3. My radius is 4. My theta is 5 pi over 3. All right, so x is equal to r cosine theta. So I have 4 cosine 5 pi over 3. On the unit circle, 5 pi over 3 is in quadrant 4. So that means cosine will be 1/2. So I have 4 times 1/2, which is equal to 2. And then I have y, which is equal to r sine theta. So 4 sine theta, 5 pi over 3. The same coordinate for sine will be -√3 over 2. So I have 4 times -√3 over 2. The 2's will cancel, or the 4 and the 2 will cancel, so I get -2√3. So that means our rectangular coordinate will be 2, -2√3. Again, you should be using exact whenever possible. Don't go straight to the calculator. All right, the last example is going to be C. My r is -3. Theta is equal to 7 pi over 6. X is equal to r cosine theta, so -3 cosine 7 pi over 6. On the unit circle, 7 pi over 6 is in the third quadrant, so I'll have -3 times -√3 over 2, which is equal to 3√3 over 2. And then y will be -3 sine theta, which is equal to -3. This will be -1/2. So we get +3 over 2. So xy rectangular will be 3√3 over 2 and 3/2. So if we think about sketching this one, running out of space, I go -3, so I travel to the left, and then I open up counterclockwise for 7 pi over 6. That's going to push me, whoops, not a straight line. So 7 pi over 6 is just past pi, so it'll push me here. So that's why the x and y coordinate are positive, is because we are actually in quadrant 1, because we are opening counterclockwise from a negative radius. All right, that's converting from trig to rectangular. We can also go from rectangular to trig, and you're going to use the same formulas we used in complex numbers. So you're not learning much of anything new. We're just doing it in a different plane. All right, so you do need to remember your Pythagorean theorem. When we wanted to solve for r, we had the square root of x squared plus y squared. When we solved for theta, we would use tan beta is equal to the absolute value of y over x. And then depending on what quadrant you're in, beta is equal to theta. In quadrant 1 or 2, we did 180 minus beta. Quadrant 3, we did 180 plus beta. And then in quadrant 4, we did 360 minus beta. So we are continuing exactly what we did from the last few units, all right? So this should be pretty okay for you. Convert the following points from rectangular to polar. So now we have x is equal to -2, y is equal to +2. So that means we need r and theta. So r is equal to the square root. I'm going to have -2 squared plus 2 squared, which is equal to the square root of 4 plus 4, which is equal to the square root of 8. So again, you should always draw a quick sketch so you know what quadrant you're working in. -2, 2, I'm going to be here. So we're in quadrant 2. So that means tangent beta is equal to the absolute value of y over x. So we have 2 over 2. Which tangent beta, that's just going, oopsie. So that means we are going to have beta is equal to inverse tangent of 1, which is equal to inverse tangent of 1 is going to be pi over 4. Now we're dealing with standard angles. So I technically have, if I'm in quadrant 2, I have pi minus pi over 4. We can think of 4 pi over 4, which is equal to 3 pi over 4. Or if you're like, oh, it's 1, like it's a standard angle, we're in quadrant 2, for tangent, that would be 3 pi over 4. You can do that as well. So we have our r, we have our theta. So this is theta is equal to pi minus. I'm using that reference triangle with beta. So when you list your coordinate, it's r theta. The output is first, which is root 8. The input is second, which is 3 pi over 4. So with the rectangular -2 up to quadrant 2, same thing with this. If I go out with a radius of root 8, I open up 3 pi over 4, I end up in quadrant 2 as well. Part B, we have 1 negative root 3. If I graph this, we are in quadrant 4. So x is equal to 1, y is equal to negative root 3. To find the radius, we use Pythagorean theorem. So I have 1 squared plus, the negative's going to go away anyway, so I'm just not going to include it. So we end up with 1 plus 3, which equals the square root of 4, which equals 2. So we have a radius of 2. Now, if I have a radius of 2, I have my coordinate. Just like in complex numbers, I know that my radius is 2, so I can divide both of these coordinates by 2. So that means I get 1/2 and then negative root 3 over 2 on the unit circle. And I only did this because I knew that 1 and root 3 were standard numerators on the unit circle. Now we're dividing or have a radius of 2. Hello, it's going to be the same angle. Okay, so from here, if I go 1/2 and then negative root 3 over 2, you're going to end up at 5 pi over 3. And remember, you want your angles to be from 0 to 2 pi or 0 to 360. Try to stay within 1 revolution. Now, something else you could have done, you could have used tangent beta again, but these little shortcuts will help you get through these quicker. Okay, so we have r theta is equal to, our radius is 2, our angle is 5 pi over 3. And lastly, we have 0, -5. So you are not required to show all the work for all of these. I know x is 0, y is -5. If I want to get to this point in polar, there's multiple ways to do it. However, we want to try and stick with positive radius and then an angle that's from 0 to 360, okay? Now, if I were to switch to polar, think of drawing a circle here. If I had a circle, the radius would be what? From the center, we travel -5, so there would be a radius of 5. And if we think of our unit circle, the angles do not change. No matter from radius of 1, radius of 5, the angles will be the same. If I think about the unit circle here, what's that? Theta? That is pi. That is angle pi, or 180 degrees. Well, I switched. Hopefully you were yelling at me while I was doing this video. I switched my x and my y. I even wrote y is -5. My dot, my point, my coordinate should be down here. Yikes. So x equals 0, y equals -5. But we can still apply the same idea. I have a circle here. The length here is 5, so we have a circle with a radius of 5. And then this angle, if I start from 0 degrees, that is going to be 3 pi over 2. Sorry about that. So that means our coordinate is 5, 3 pi over 2. All right, and then the last note is that for rectangular, the coordinate 0, 0 is a fixed starting point at the center of the Cartesian coordinate system called the origin, meaning x equals 0, y equals 0. It's the only way to represent the origin. However, in polar, the coordinate 0, theta is a fixed starting point at the center. This is called the pole, meaning the radius is 0, no matter what the angle is. So if I had 0, 60 degrees, we're at the pole, we're at the center. If I had 0, 3 pi over 2, you're at the pole, you're at the center. There is an infinite number of ways to stay at the center of the polar coordinate grid. However, for Cartesian, there's only one, it's 0, 0. So again, we're playing with that multiple representations for each of these points, which you have to start getting comfortable with. And then I found another cool, this is the last thing I'm going to show. It's a cool way to show Cartesian versus polar. You can animate it slowly or you can animate it quickly. In the next lesson, we're going to start talking about polar graphs, and we're going to compare them to Cartesian, but I'm going to start straying away from Cartesian sooner than later. So we're going to talk about relating these and how they look to sinusoidal curves versus the petals and flowers that we're going to see in polar. All right, I hope this video was helpful. Please make sure that you get ready for the assignment in class, and I will see you in the next video.